Welcome to the video lecture on cylindrical shells. Now take a look at this first example here. We want to find the volume of the solid formed by revolving the region bounded by the graphs y equals x squared plus 1, y equals 0, x equals 0, and x equals 1 about the y-axis. So this is a volume of revolution problem. So first thing we're going to do is draw the region that we're talking about that's being bounded, and then we're going to rotate it around the y-axis. So let's start by drawing y equals x squared plus 1. That's just a parabola that's been shifted up 1 unit. Y equals 0 is just the x-axis. X equals 0 is just the y-axis. And x equals to 1 would be just a vertical line at a height of 1. So we don't actually want both sides of this parabola because the region that's bounded by the x-axis, the y-axis, the parabola, and this vertical line is just the piece in this first quadrant. So I'm going to go ahead and take away that left side, and this is the region that we're talking about. And now that we know what we're going to rotate, let's go ahead and rotate it around the y-axis. So the mirror image would come over here and look like this. Now, so far up until this point, we've learned how to do problems like this using the disc and washer method. So let's see what happens when we try that here. Because our axis of revolution is the y-axis, which is a vertical axis of revolution, we want to take our discs or our washers perpendicular to the axis of revolution, which means they would need to go horizontally. Now we have a little bit of a problem here because it depends on where you draw that disc or washer as to what's going to happen. If I draw a cross section down here, you get a nice solid disc and you want the volume of that entire circle. But if I draw one up here, I don't want a solid disc. I actually want a washer because there's a hole in the middle. So it depends on where we are as to what method we have to use. And what is the dividing line that determines when this change happens? Well, it's going to be wherever this hits right here, which is this y-intercept of our parabola. So right at 1, the switch changes. Below 1, we can use nice solid discs, but above 1, we would have to use washers because we're going to get a hole in the middle. So let's go ahead and write out what these would look like, these volume integrals. For the solid disk, we would need to know the radius, so we need to know the center point and the side point over here. Those both share the same y coordinate, so they're both going to have a y coordinate, which I'll just call y. The center point is on the y-axis, so its x value is 0. And the side point over here is on that line x equals 1, so its x value is always 1. So the radius going across here would just be this rightmost x value minus this leftmost x value, which is just 1. So for these discs down below, the volume would be the integral of pi r squared, and because these are horizontal discs intersecting the y-axis, this would be a dy integral. And for this particular problem, our r is 1, so this would become pi times 1 squared dy. And the bounds that I would use for y, remember we want to stop when we get to 1 because then we switch to washers. So our bounds for y would be from 0 up to 1. So this is just the integral of pi dy from 0 to 1. Now let's take a look at what we get up here. This is going to be a washer up here, so we need pi times the integral of big R squared minus little r squared. And again, they're going horizontally, intersecting that y-axis, so this would still be a dy as well. Let's figure out what our big R and our little r are going to be. So we need the center point here, this middle point here, and this outer point over here. They're all at the same height, so they all share the same y value. The center point is on the y-axis, so its x value is 0. The middle point is on our curve, so we want to use this curve. but I can't use x squared plus 1 because this is a dy integral. I need to know what x is in terms of y. So we would have to solve this for x. So I'm going to subtract 1, and then I'm going to take the square root of both sides. You do get a plus or a minus case, but because we're in quadrant 1 over here, we're going to use just the plus case. So this would be square root of y minus 1. And then the outermost point over here is on that line x equals 1, so its x value would be positive 1. So big R is from the outermost x to the center x, so 1 minus 0, which is just 1. The little r is from the center, or excuse me, the middle x value, which is our square root of y minus 1, up to the center, which was 0. So that will be square root of y minus 1. So this integral becomes pi times that big R, which was 1 squared, minus the little r, which was that square root of y minus 1 squared, all of that times dy. And what are the bounds that we want here? Well, we want to start at a height of 1, and we want to go up to here. Now, what's that going to be? Well, that's the intersection of this parabola and the line x equals 1. So if x is 1, 1 squared plus 1 would be 2, so this is at a height of 2. So I want to go from 1 to 2. So the total volume of this whole shape would be the discs on the bottom, which were from 0 to 1 pi dy, plus the washers on the top, which are pi times the integral from 1 to 2 of this 1 squared minus square root of y minus 1 squared dy. Now those aren't impossible to solve, but the fact that we have two different integrals to do makes this sort of a tedious process and makes the problem harder than potentially it needs to be. So what we're going to learn about today is a new method to deal with situations like this, where we use something called cylindrical shells instead of using discs and washers. And one of the key differences is that instead of taking the cross sections perpendicular to the axis of revolution, what cylindrical shells are going to do is take the cross section parallel to the axis of revolution. And this is called the cylindrical shell method. So here's that same picture that we had before, and this time what I'm going to do is I'm going to take a little slice parallel to the axis of revolution. So if our axis of revolution was the y-axis, then parallel to that means I'm going to take a little slice going up and down vertically, just like the axis of revolution is. And then what I'm going to do is I'm going to take that slice and then I'm going to rotate that slice around the y-axis. So we draw in its mirror image, and then we connect the top with the circle to show that sort of cylinder shape. And this cylinder has a little bit of thickness to it. And that thickness is coming from the fact that our initial slice is intersecting the x-axis here. So you've got a little thickness along that x-axis. So this is going to be a dx integral. Okay? So if we have our volumes here, what you want to think about, the volume that we're talking about, is the volume in just the shell of that cylinder. If you imagine kind of like a paper towel roll, where the volume is just in that thickness of that cardboard going around. That's what we're talking about here. What we really have are a bunch of these shells sort of stacked or nested inside one another. So you would have like a little shell here, and then another one that's bigger, and then another one that's bigger, and the volume is coming just from that little shell part. If you've ever seen those cups that sort of collapse in on themselves for things like camping, if you're ever a Boy Scout or a Girl Scout and had one of those cups that collapses in on itself, that's kind of what we're talking about here. We have these shells that stack within each other, and when you put all those shells together, they eventually fill up this whole volume. Okay? So what we need to figure out to come up with sort of a formula for this is we need to find out what the volume would be in one of these little cylindrical shells. So to figure that out, you would need to know the surface area of the shell times its thickness. So the surface area of the shell would be the circular circumference times that height. So circumference is just 2 pi r, and that height is what we're calling h. So the surface area of our shell is 2 pi r h, and that means the volume is 2 pi r h, that area, times our thickness. So this is going to be the little volume that we get just from that one shell. If we add up all those little shells and we accumulate them and sum them all up, then these become a definite integral. And this delta x becomes our dx, and what we're integrating is 2 pi r h dx, and then our bounds would be whatever x changes from. Okay, so this is going to become our formula for cylindrical shells. It's called the cylindrical shell method, and what you're going to have as your formula is the volume of 2 pi r h times dx, or potentially 2 pi r h times dy, depending on which way your shell goes. So here's what the volume formula looks like. The integral of 2 pi r h, and it will be either dx or dy. You're going to use the dx's when your shells are vertical. So they would look like this. You're going to use dy's when your shells are horizontal, like this. And the way you determine which way your shells go is you always want to take your cross sections this time parallel to the axis of revolution. In the disc and washer method, we always took our cross section perpendicular to the axis of revolution. So here we're going to take it parallel, and based on that, that will determine whether or not our thickness, our height, is intersecting that x-axis or that y-axis, and that will determine if we have a dx or a dy integral. Now when you're finding these, you're going to need to know what the radius is, which will be this little r going across here, and your height, which would be this height here. In the horizontal case, your radius would be that little distance going across, and your height would be this h going across like that. What I usually recommend for students is that you find the height function first, either in terms of x's or y's, depending on which way you're supposed to do it, and then the radius is usually just x or y, unless you have some kind of translation involved where the axis of rotation is something other than one of the major two axes. And I'll show you examples of that in a moment. Okay, so this is called our cylindrical shell method. So let's take a look at some examples. Find the volume of a solid of revolution of the region formed by y equals 1 minus x, the x-axis, and the y-axis, and we're going to revolve it about the y-axis. So step 1, draw your bounded region first so that you can see what it is that you're talking about. So we have the curve y equals 1 minus x, which is just a line with a y-intercept at 1, an x-intercept at 1, and it's just going to look like that little line segment if we're also bounded by the x-axis and the y-axis. So we're talking about that little triangle. And we want to rotate this around the y-axis just like that. Okay? So let's draw in the mirror image just like we've done in the past. And this time you could certainly use the disc method here because the cross sections perpendicular to that y-axis are nice solid discs. But I want to show you how to do this with shells as well, since that's our new method for today. So to draw in your shells, you want to take your cut or your slice parallel to the axis of revolution. So our axis is vertical, so my slice should be vertical. So draw in a little slice just like that. Then you're going to draw its mirror image, and then you're going to connect the top and the bottom with circles. There's your cylinder. Okay, so because this is a vertical cylinder that's intersecting that x-axis, this is going to be a dx integral. So our volume formula is going to be the integral of 2 pi rh times dx. So we need to figure out the r and the h in terms of x's. Now to do that, you need some points to worry about. Your height is going to come from these 2 points, and your radius is going to come from the center out to either one. And you can either do this center point or you could do this one down here. It doesn't matter. It'll give you the same value. I'll just do the top one. So I like to do the height first. If you look at these 2 points that would determine the height, what do they share in common? They both have the same x coordinate. The bottom point is on the x-axis, so its height is 0. The top point is on our line, so what's the y value of the line? Well, y is 1 minus x, so this y value is 1 minus x. So my height is this top point minus this bottom point, so 1 minus x minus 0, which is just 1 minus x. So always find your height first. Now we're going to find our radius. The radius is going to be determined by this horizontal distance right here. Now these 2 points actually share the same y value, and we already know what this y value is of this point, so this one would also be 1 minus x. It actually doesn't even matter that you write that in there, because to find this radius, we're just worried about the x's, because this distance here is the difference in the 2 x's. So you don't even really need to know what that y coordinate is, you just need to know what the x coordinate is, and since it's on that y-axis, the x coordinate is 0. So the radius is going to be this x value minus this x value, the right point minus the left point. And that's just x. And usually in these problems, the radius is either x or y, or some shift of that, depending on what your axis of revolution is. Okay, we know h, we know r, we're ready to plug them in. So this becomes 2 pi times r, which was the x, times h, which was 1 minus x. And then we want our bounds for x. Now this one is tricky. You want to be a little bit careful here. You want to use the bounds for x of the original bounded region. Don't use the entire mirror image as well. So if you remember in our initial graph, this was our bounded region. So the bounds for x here are from 0 up to 1. We don't want to go all the way from -1 to 1, because then we're double counting some of those shells. We just want to go from that y-axis out to 1. So be careful on that. You want to know what your radius is going to vary between, and it starts with a radius of 0 out to 1. So here's my volume integral. Let's go ahead and integrate. Let's pull out the 2 pi. I'm going to go ahead and distribute my x, so this is x minus x squared dx. So the integral of that becomes x squared over 2 minus x cubed over 3, and I'm going to plug in my bounds. So I'm going to get 2 pi times 1/2 minus 1/3. When I plug in my 0, I'll get zeros. And that gives me 3/6 minus 2/6, which is 1/6 times 2 pi. And that is going to give me pi over 3. Okay? All right, so now let's take that same region, but this time we're going to revolve it around the line x equals to 4. So we're going to take this same initial region, and we're going to rotate it around the line x equals to 4, which is all the way out here. So when you rotate this around the line x equals to 4, the mirror image, when I flip this over, is going to be way over here. Okay? Now this one has obviously a hole in the middle. So if you were going to do this with discs and washers, you'd have to use a washer. We're going to do it with shells, and that's the nice thing about shells, is that shells work no matter what. They work when discs would work, they work when washers would work, and they work when you'd sometimes have to use both discs and washers. So it's a more powerful method sometimes, though it does have its faults, which we'll talk about in a little bit. So how do we draw in our shell? Well, you want to take your slice parallel to the axis of revolution. So my axis is vertical, so my slice needs to be vertical. And I'm going to draw its mirror image, and then I'm going to connect the top with the circle and the bottom with the circle, and there's my little shell shape. Because this axis of revolution was vertical, my slice was vertical, it's intersecting that x-axis, this is going to be a dx integral. So we're going to need 2 pi rh times dx. I like to recommend starting with the height first. So going back to the original bounded region over here, the height would be determined by these 2 points and that vertical distance. So let's find these 2 coordinates. They both share the same x. The bottom point is on the x-axis, so its height is 0. The top point is on the line, and the equation of the line was 1 minus x. So the height is this top point minus this bottom point. So it's the same height that we got before. Okay? The radius is what's going to be different because our axis of revolution is not the x or the y-axis. It's actually x equals 4. So we're going to have a little bit of a shift going on here. So to get the radius, you need one of these center points, and you can either do the one on the top or the one on the bottom. It doesn't matter which one. I'll just do the bottom one this time. And the radius is going to be this horizontal distance going across, which is dependent only on the difference in the x values. So what's the x value of this center point? It's on the line x equals 4. I don't really care what the y value is because I just need to know this right point minus this left point. So the radius is going to be 4 minus x. Usually the radius is either x or y if your axis of revolution is just the x or the y axis. If your axis is not and it's shifted over, then your radius will be shifted over as well. Okay? So now we know r, we know h, we're ready to set up our integral. This will be 2 pi times the radius times the height. And then my bounds, remember the bounds should be the bounds of the original region, which was this shape right here, which ranged from 0 to 1 for the x's. So just do from 0 to 1. Okay? And then you can use function integrate on that. You can FOIL it out however you want to do it. I'll leave that work up to you, but this becomes 11 pi over 3. Okay? All right, one last variation on this. We're going to take that same region, and this time we're going to rotate it around the line x equals -1. So the mirror image would look something like this. The axis of revolution is vertical. So if we're going to do shells, we want to be parallel. So we also want to be vertical. So you're going to do a little slice up and down just like that. And then it's mirror image. Connect the top and the bottom with circles. Since this is up and down, vertical, intersecting that x-axis, this is another dx integral. So 2 pi rh dx. So to get the height, I'm going to go back over here and find these 2 points to find that vertical distance. They line up, so they both share the same x value. The point on the bottom is on the x-axis, so its height is 0. The point on the top is on that line, which had as its equation 1 minus x. So the height is 1 minus x on top minus the bottom 0. So the height function is still 1 minus x for all 3 of these problems. The only thing that's changing for these 3 is the radius because my axis of revolution is being moved around. So how do we find the how do we find the radius? We need a center point. So let's say we take that one. This distance here is determined only by the x's. So this x value right here, since it's on the line x equals -1, would just be -1. I don't even need to know what that y value is, because I just want this right x value minus this left x value. Be careful with your negatives. We're going to take the rightmost point, which is the x, minus the leftmost x, which was -1, so this actually becomes x plus 1. So now we know our r and our h, so this becomes 2 pi times x plus 1 times h, which is 1 minus x, and the bounds of the original region were 0 to 1. So those bounds stay the same throughout all three of these problems. Okay, and then I'll go ahead and solve this one for you. You could pull out the 2 pi. When you FOIL this out, you're going to get an x, a minus x squared, a plus 1, and a minus x. So the x's cancel, and this is just negative x squared plus 1. So when you integrate that, you get negative x cubed over 3 plus x. So when I plug in 1, I'm going to get negative 1/3 plus 1. When I plug in 0, I'll get 0. Negative 1/3 plus 1 is 2/3. 2/3 times 2 pi is 4 pi over 3. So all three of these were very similar. The only differences were the r's, based on whether I was subtracting x from 0 or 4 or -1. And I had that shift in that axis of revolution, so I had that shift in the radius as well. Okay, on the next example, we want to find the volume of a solid of revolution of the region in the first quadrant formed by y equals x squared plus 4, y equals 8, and the y-axis, and it's going to be revolved around the y-axis to start. So if we draw this region that is being bounded, we're going to start with that parabola, y equals x squared plus 4, which is just a parabola that's been shifted up 4 units. And then y equals to 8, since this is starting at 4, y equals to 8 would be somewhere up here. And the y-axis. And we want this just in the first quadrant. So we're just talking about this piece of the parabola, the y-axis here, and that horizontal line, so that sort of triangular region. So I'm going to get rid of that left side for now. So that's our bounded region that we're talking about, and we want to rotate this or revolve it around that y-axis. So I'm going to draw in the mirror image, and then if I'm using shells here, discs would also work because the cross-section perpendicular to the y-axis is a nice solid disc, so that would be an easy way to solve the problem. But if we're going to practice shells, then in our shell method, we want to take our slice parallel to the axis of revolution, and our axis is vertical, so we want to take a slice that's vertical as well. So it would look just like that in our region. The mirror image over here would look like that. Put a circle on the top and a circle on the bottom, and now we have our shell. So since this is vertical, if you were to extend this down, that slice would eventually intersect that x-axis. So that means this is going to be a dx integral. So our formula will be volume equals the integral of 2 pi rh dx. So we need to find r and h in terms of x. So let's start with that height. Always find that height first. That's going to be determined by these 2 points and this vertical distance here. So let's find these 2 coordinates. They share the same x value. The upper point is on that line y equals 8, so its y coordinate is always 8. The bottom point is on our curve, and the curve is y equals x squared plus 4, and that formula is already in terms of x, so I can just use x squared plus 4 for that y value. So the height is going to be the top y value, top height, minus the bottom height. So this 8 minus this x squared plus 4, and use parentheses when you subtract, so that when you distribute the negative, this height function becomes 4 minus x squared. Now let's find our radius. So to get our radius, we need a center point. It doesn't matter whether you do it from the top circle or the bottom circle. I'll just do it on the top circle. And this point has as its x-coordinate 0 because it's right on that x-axis. The y-coordinate happens to be 8, but it doesn't really matter what that y-coordinate is because we want to look at these two x's to get that horizontal distance going across. So the right endpoint would be this x, the left endpoint would be the 0, so the radius is going to be the x minus 0 or just x. So now we have our height and our radius, so let's plug them in. This is going to become 2 pi times the radius, which was x, times the height, which was 4 minus x squared. And then our bounds need to be x bounds. And remember, this should be the bounds for x of just the original region before we rotated it. So that was just this region in that first quadrant. And that obviously starts at 0 for x, and then we need to find out how far over this goes. And that's going to be determined by where this parabola intersects y equals 8. So where these two things are equal. So if I set the parabola equal to 8 and subtract 4, taking a square root gives me plus or minus 2, and we're in quadrant 1, so that's going to be the plus 2. So my bounds are from 0 to 2. So there's my integral. To solve it, pull out our 2 pi. I'm going to go ahead and distribute my x across, so I get 4x minus x cubed dx. And if I integrate 4x, I'm going to get an x squared over 2, but that 2 on the bottom goes into the 4 on the top and just gives me a 2 all over, so it's 4 over 2 reduces to 2. And then x cubed becomes x to the 4th over 4, and we're going to plug in 0 and 2. So when I plug in 2, 2 squared is 4, 4 times 2 is 8, 2 to the 4th over 4 is just 4, and then I'm going to subtract 0. 8 minus 4 is 4, 4 times 2 pi gives me 8 pi. So there's my volume. Okay, now we're going to take that same region and we're going to rotate it around the vertical line x equals to 4. So let's draw our initial region. Here's our parabola and our line y equals 8. And we want to rotate this around the line x equals to 4. Remember, this goes out to 2 based on our intersection point up here. So 4 is going to be some distance away from that. So when I rotate this, the mirror image on the other side would look kind of like that. Now this obviously has a hole in the middle, so you could use washers. We're going to try shells again. Since my axis of revolution is vertical, my slice needs to be vertical. So in the original region that would look like that. The mirror image would be over here. Connect the top with the circle and the bottom with the circle. So there's my shell. The slice here is vertical intersecting that x-axis, so this is going to be another dx integral. So volume equals the integral of 2 pi rh dx. So let's find that height first. I'm going to go back to the original region, not the mirror image. So I'm going to go over here and I'm going to find these two endpoints so that I can find that vertical distance. So I need to know these two coordinates. They line up, so they both share the same x. The top point is on that line y equals 8, so its height is 8. And the bottom point is on our parabola, which had as its equation x squared plus 4. So the height function is this top minus this bottom. So that's exactly the same height function that we used in the last example. So when we distribute the negative across, we get that height is 4 minus x squared. So that hasn't changed. What's going to change is our radius, because our new axis of revolution is no longer either the x or the y axis. It's been shifted over. So our radius is going to be shifted as well. It's not going to be a simple x like it was before. It's going to involve this 4. So to figure the radius out, pick a center point, doesn't matter which one. If I pick this one, this has an x value of 4, and it just so happens that the y coordinate would be 8, but you don't have to use that y coordinate at all. We're going to use this rightmost x minus this leftmost x to get that horizontal distance across. So this x minus this x tells me that the radius is 4 minus x. So notice that this radius is no longer just a simple x, it's been shifted because of that 4. All right, we're ready to plug in. I'm going to take 2 pi times my radius times my height. And then my bounds here, again, the original region was this region, and the bounds for x of that region were 0 to 2. So here's my integral. And I'll leave it to you to go ahead and solve it. You would want to FOIL this out and then integrate term by term. And I believe that the final answer comes out to 52 pi over 3. Okay? All right. Same region. So we're going to take the same region that we had before. This time, we're going to rotate it around the line y equals to 9. Actually, I'm going to lower this down because 9 is going to be kind of up there. So let's draw it a little bit lower. Here's my region. Here's 4. Here's 8. So y equals 9 is a horizontal line at a height of 9. So when I rotate around that axis, this is going to flip over and the mirror image would look something like that. So this time my axis of revolution is horizontal. So in the shell method, my slice needs to be parallel to that. So my slice should also be horizontal. So it would have to look something like this. And then the mirror image would be over here. Connect these with circles and these with circles. There's my shell. Now this time, because my slice was horizontal, it's intersecting that y-axis. So this needs to be a dy integral. So my volume is going to be the integral of 2 pi rh dy. So now everything needs to be in terms of y's. So let's start with our height. I'm going to go back to my original region over here, and I need these two endpoints to find the length of that slice, that initial slice that I drew in. That's always your h. So we need these two coordinates. Now they both share the same y. So this time the y is what's in common. This point is on the x-axis, so its x-coordinate is 0. This point is on my curve, which remember was y equals x squared plus 4. But unfortunately, that formula is in terms of x's, and this time around we need y's. So I'm going to need to solve this for y. So if I subtract 4 and take a square root of both sides, you get that plus in that minus case. And in the quadrant 1 here, the plus case is what we want for this right-hand side of our parabola. So we want the positive square root of y minus 4. The negative case would be the other half of the parabola over in quadrant 2, which we're not looking at. Okay, so my height then is going to be the right x value minus the left x value. So this minus 0. So my height is just going to be square root of y minus 4 minus 0, or square root of y minus 4. Okay, now we know our height. Let's find our radius. So let's pick a center point. If I pick my center point up here, then what I need, whoops, I drew it in the wrong spot there. If I pick my center point right on that axis of revolution, I want this distance right here for my radius. So we need to know the x and y coordinates of our point here. The x coordinate is just going to be 0 because we're on that x or that y axis, and the y coordinate is the axis of revolution, which is that y equals 9. So this is at a height of 9. So to get this vertical distance right here, we need this y height minus this y height. So this y coordinate 9 minus this y coordinate y. So the radius is going to be the top 9 minus the bottom y. So again, that radius is not just an x or a y. In this case, it's been shifted by that axis of revolution, which was at 9. Okay, we're ready to plug in. 2 pi times our radius, which is 9 minus y, times our height, which is the square root of y minus 4 dy. And we need bounds here. Remember, this is the original region we started with before we rotated it. And this is a y integral. So what are the y bounds here? We can see that y starts at 4 and goes up to 8. Don't go all the way up to 9. Go up just until that bounded region. So here my bounds should be from 4 to 8. Now this particular integral is a tricky one to solve until we've learned some new techniques. So this would definitely be a good candidate for that function integrate command on your calculator. And you would type in all of this for your integrand. If you want to include the 2 pi in there, you can, or you can just multiply the answer that you get for the integral times 2 pi at the end. It doesn't matter how you do it, but the approximate value of this integral is about 87.13 units. Okay? All right. Next example, find the volume of a solid of revolution of the region formed by 1 over x squared, x equals to 1, x equals to 4, and y equals to 0. And we want to revolve it around the x-axis. So you can certainly graph this on your calculator if you like. 1 over x squared looks kind of like this. X equals to 1 is a vertical line. X equals to 4 is a vertical line. And y equals to 0 is just that x-axis. So the region bounded by these 4 curves is this shape right here in the middle. Okay? So we want to rotate this around the x-axis. So the mirror image would look something like this. Okay? Now, on this particular example, I want to show you 2 options here. The shell method, if you were to do that, would require that you take your slice parallel to the axis of revolution. So if our axis of revolution is horizontal, then our slice needs to be horizontal. Now I want to show you why the shell method is probably not the best choice here, because look at what happens when I draw my slice. If I draw it over here, then the mirror image would be over here, and we'd have something that looks like this. Now if we go to find this height, we're going to need this point and this point, and that would be determined by the curve on the right side and this vertical line x equals 1 on the left side. So these 2 points share the same y coordinate. The point on the left is at x equals 1, and the point on the right is this curve. But we can't use 1 over x squared because since this slice is horizontal, it's intersecting the y-axis, the shell method would have to use a dy integral. So that means we need to use y variables only. So I would need to take y equals 1 over x squared, and I would need to solve that for x. So if I multiply both sides by x squared to get rid of my fraction, divide by y, and then take a square root of both sides, I'm going to take the positive square root because we're in quadrant 1, then the x coordinate of this point is square root of 1 over y. So my height would be this x value minus this x value. Then the radius would be from here to here, and that point down here at the bottom in the center of my circle has an x value of 1 and the y value is 0 because it's on the x-axis. So this vertical distance here is going to be this y value, which is just y, minus this y value, which is just 0. So the radius would just be y. So our volume would start out with 2 pi rh dy, and so this would be 2 pi times the r, which was y, times this h, and then some bounds. Now before I finish those bounds, I want you to notice something. What happens if I take my slice down here? Now the mirror image would be over here, and I would get some circles like this. On the right, what am I bounded by? I'm bounded by 4. And on the left, I'm bounded by 1. Whereas up here, I was bounded by the curve on the right and 1 on the left. So it's not consistent. So if we did it this way, if we looked at this slice, and we looked at these 2 points, again, they share the same y, but this x value is 1 and this x value is 4. So when I do right minus left, the height is actually 3 this time. And what would be the radius? Well, the radius is still going to be y, because this point here in the center, it's getting a little crowded here with all my scribbles, but if I look at the center point here, this would just be at 0, 0, and that would mean that this vertical distance would be this y value, which is y, minus this y value, which is 0. So the radius would still be y. What's different between my red cylinder and my green cylinder is the height function. The green cylinder always has a constant height of 3, whereas the red cylinder has a height that's changing depending on where I am on the curve. So for this green case, my volume integral would be 2 pi times the r, which was y, times the height, which was 3. So we actually need 2 different integrals, and we would need to add the 2 cases together to get the full volume. Now, what are the bounds? Well, the bounds are going to depend on where this change happens, and the change happens right where the curve intersects 4. So where does 1 over x squared, where does that curve intersect x equals to 4? Well, if I plug in 4, 1 over 4 squared is 1/16. So this is at a height of 1/16. So the red cylinders should have bounds starting at 1/16 and going up to this point here, which is when x is 1, and 1 over 1 squared is 1. So the bounds for the red cylinders are from that 1/16 up to 1. For the green cylinders, that's starting at a height of 0 up to that 1/16. And we're not going down in the negatives at all, because remember, the original region was just in that first quadrant. So from 0 to 1/16 for this green integral, and then from 1/16 to 1 for this red integral. So here's what we would get using the shell method. Certainly it's doable, but it's a big mess because you've got a yucky function in here to integrate, and you've got 2 separate integrals that you have to solve. So is there a better option? Yes. If instead we take a look at this region and we rotate it around that that x-axis, what we could notice, instead of taking our slices horizontal, which might change depending on where we draw it, what if we take our slices vertically or perpendicular to that axis of revolution? Then they're going to have the shape of a circle. And over here, I'm bounded between the curve and the curve, the curve and the curve, the curve and the curve, the curve and the curve. So it doesn't seem to matter where I draw that disc. It's consistently the same on the top and the bottom. So what that's good for is it tells me I can just use the disc method. Don't use shells, use discs instead, because I can get away with using only one integral if I use the disc method instead of the shell method. So if we do the disc method, we would need to know these 2 coordinates. They share the same x. The bottom point is on the x-axis, so its height is 0. The top point is on the curve, which had as its equation 1 over x squared. So the radius is this y minus this y, or just 1 over x squared. And because this disk is vertical, it hits the x-axis. This is going to be pi r squared dx for the disk method. It's going to be a dx integral. So this is going to be pi times my radius, which I found out to be 1 over x squared. We want to square that. And then my bounds for x, well, this was from 1 to 4. So this is a much simpler integral to solve and to evaluate than these two up here. And the answer to this, if you solve it out, is 21 pi over 64. So you need to be really careful when you're doing these problems as to what would be the most efficient, easiest way to solve them. And sometimes disks work, sometimes shells work, sometimes washers work. It depends on the graph. In some cases, you might have to use 2 integrals versus 1 based on the way you take your slice. So depending on whether or not you need 2 integrals or not, go with the option that only requires 1 integral because it will be less work. Okay, let's take that same region, which looked kind of like this, from 1 to 4, and this time we're going to rotate it around the y-axis. So I'm going to rotate it, and the mirror image would look kind of like this. So let's keep in mind here what would be the best approach. If we tried to do this with washers, which we would have to use because there's a hole in the middle, washers would not be the best choice here because let me draw over here what it would look like. If you take a washer, you have to take your cross-section perpendicular to the axis of revolution. So the axis is vertical, our washer should go horizontal. If I draw my washer up here, the outer circle goes from the curve in, and the inner circle goes from this vertical line in. If I draw my washer down here, the outer circle goes from the vertical line in, and the inner circle goes from the inside vertical line in. So this point is on the curve, but over here this point is on the line. So you'd have to use 2 different integrals at that dividing point again, and you'd use washers for the top part going from the curve in, and you'd use washers on the bottom part going from 4 in and 1 in. Okay, so this would require 2 integrals. We don't want to do that. That's too much work. So instead, we try the shell method. And the shell method allows us to take our cross sections parallel to the y-axis, which would mean up and down. So if I go up and down, if I'm here, I'm doing curve to the x-axis, curve to the x-axis, curve to the x-axis, curve to the x-axis. It's consistent, and that's what I want. That means I'm only going to need 1 integral to do this problem. So if I draw the mirror image over here, a typical shell would look like this. So I can get away with only 1 integral, and because this is a vertical slice hitting the x-axis, this is a dx integral. So my height will be determined by the height of this slice right here. So I need these 2 points. They share the same x. The bottom point has a height of 0. The top point is the curve, and the equation of the curve was 1 over x squared. So the height is this y minus this y. So that'll just be 1 over x squared minus 0, or 1 over x squared. The radius is this horizontal distance. This inside center point has an x value of 0. So when I take this x minus this x and do right minus left, the radius will just be x minus 0, or x. So my volume becomes 2 pi times this radius, which was x, times this height, which was 1 over x squared. And what are the bounds for x? Well, the original region was this region, which went from 1 to 4 on that x-axis. So my bounds need to be 1 to 4. Now to evaluate this, I'm going to pull out my 2 pi. X times 1 over x squared reduces to a 1 over x. What function has as its derivative 1 over x? That's a special function. That's an ln. This is stuff prime over stuff. So I need for my antiderivative the absolute, or ln of the absolute value of x. So when I plug in 4, I'm going to just get ln of 4. I don't need these absolute values because my inputs are positive. Minus ln of 1, and ln of 1 is 0. So this is just going to be 2 pi times the ln of 4. Okay, same region again, so let's draw it. But this time we're going to rotate it around the vertical line x equals to 4. So when I rotate that around, the mirror image is going to look like this. Now visualize, if you were to draw in some slices horizontal, because that would be perpendicular to the axis of revolution, you would need to either have washers on top, something like this, because there's a hole in the middle. But if you drew one horizontally down here low, you could get away with a solid disc because there's no hole in the middle. So this is kind of like that very first problem we did at the beginning of this lecture. So we don't want to do that because that requires two different methods and two different integrals. So we don't want to take our slices perpendicular to the axis of revolution. Instead, we want to take our slices parallel, which means we're going to do it with shells. If I do a slice parallel, then here I am curve on top, x-axis on the bottom, curve on top, x-axis on the bottom, curve on top, x-axis on the bottom. So no matter where I draw that slice, it's consistently the same. So pick one of them, draw the mirror image, circles on top and bottom. There's my typical slice, my typical cylinder. Because it's hitting the x-axis, this is going to be a dx integral, so 2 pi rh dx. And my height is the length of this slice, so this vertical height here. So let's find these 2 points. They both share the same x. The bottom one is on the x-axis, so its height is 0. The top one is on our curve, and the equation of this curve again was 1 over x squared. So our height is this y minus this y, top minus bottom. So that's just going to be 1 over x squared. To get the radius, we need to go to the center of a circle, either the top or the bottom, and I want to look at the x values to get this horizontal distance going across. So the x value of this center point, since we're on that axis of revolution, that would be 4. So I need this x, which is just x, to this x over here. And actually, I just realized here that I'm going the wrong way, aren't I? I didn't go to my original curve. I went to my mirror image. So I'm going to fix that. Over here, I should have gone over to the left side. And I'll show you why in just a minute. It turns out that these coordinates would be exactly the same. Okay, x comma 1 over x squared, and over here this would be x comma 0. So these values are the same whether I go to the original or to the mirror image. But if I take these out of here for a moment so it's not so messy, when I look at my radius, it's going to make a difference which way I go, because in this case I want to use this x value because it's on the right minus this x value on the left. So my radius should be the 4 coming first because it's on the right minus the x on the left. And so my integral is going to be the integral of 2 pi times 4 minus x times that height, which was 1 over x squared. And the reason I want to do the 4 first is because if I'm using my normal bounds that I've been using for x, which are from 1 to 4, that's going to ensure that this is going to be a positive radius. If I didn't do it that way, if I had it x minus 4, then I'd have to use different bounds. I'd have to use the bounds for the mirror image, which you can do. It's just, something that's a little different than what we're used to. So it's easier to consistently do each problem the same way. So instead of trying to think about what my new bounds would be, let's just stick with our old bounds and go back to our original image instead of using the mirror image. And this way we're going to make sure we get a positive radius, which is going to ensure that we'll get a positive answer once we solve this all out. So let's go ahead and solve it. Pull out my 2 pi. I'm going to go ahead and distribute my 4 across. So I'll get 4 times 1 over x squared, which is 4 over x squared, and a minus x times 1 over x squared is just a minus 1 over x. And in order to integrate the 4 over x squared, I'm going to change it. I'm going to change it to 4 times x to the negative 2. So I can use my power rule. So when I integrate that, the 4 stays put, and when I add 1 to the power, negative 2 plus 1 is negative 1, and then I divide by the new power. This one, be careful, you don't want to move this up, because if you move it up to an x to the negative 1 and you add 1 to that, you get a power of 0, but then you're supposed to divide by the new power, and you can't divide by 0. So that should tell you that this is something special. This is that ln. Okay? So the antiderivative of 1 over x is the ln of the absolute value of x. And if you want, you can rewrite this guy right here as negative 4 over x, just so that it's a little easier to plug in. And I'm not going to need my absolute values because my inputs, my bounds here are positive. So this is going to be negative 4 over 4, which is negative 1, minus ln of 4. And then when I plug in 1, negative 4 over 1 is negative 4, minus ln of 1, which goes to 0. So we get 2 pi times negative 1 minus ln of 4, and a minus minus becomes a plus 4. So this is 2 pi times 3 minus ln of 4. And you can do more with that if you like. I'm just going to stop there. Okay, last example with this same region. So we're going to take our region from 1 to 4, and we're going to rotate this around the line y equals 1. Now you want to know where that is. Remember that when x, our curve was 1 over x squared, so when x was 4, this point here was at 1/16, and when x is 1, this point up here was 1. So those were my intersection points. So y equals 1 is right where these two hit, just like that. So then the mirror image is going to look something like this when I rotate it around that horizontal line. Now if I draw in some slices here, we need to decide which method we want to use. There is a hole in the middle, so we either need to use washers or shells. If you tried shells, you would have a little bit of an issue, because if you drew your slice up here, then we're between this vertical line, which is at 4, and this vertical line, which is at 1. So that height, that distance, would be 3. And then you would have your shell down here, and you'd have something that looks kind of like that. But if you drew a shell slice down here, then you're on the curve on the right side and 1 on the left. So your height function is something different when you look at this green shell. So you would need to have a different volume integral for all the green shells, which would be all along this curvy part, and then as soon as you hit that 1/16, anything below that is going to be the ones where the height is always 3, from 4 to 1. So doing it with shells would require that you have 2 different integrals. And we don't want to create more work for ourselves, so we're not going to do it that way. We're going to use washers instead and hope that that works out for us. So let's draw in what our washers would look like. If we do washers, washers go perpendicular to the axis of revolution. So our axis is horizontal, perpendicular would be vertical. So our washer would look like this over here. Or if I drew some over here, are those consistent? Yes, because the big circle goes from this top line to this bottom line every time. And the inner circle goes from this top curve to this bottom curve every time. So it's consistently the same, which means I can get away with 1 volume integral. And because these are going vertically, they're intersecting that x-axis, my volume integral is going to be pi times big R squared minus little r squared, and it's a dx integral. So let's get some coordinates. If I look at this one, I'm going to go back to the original curve. So I'm going to go to these 3 points right here. The center, the inside circle, and the outside circle. They're all lined up, so they all have the same x. The bottom one is on the x-axis, so its height is 0. The middle one is on the curve, and the equation of the curve is 1 over x squared. And the top one, or excuse me, the center one, is on our axis of revolution, which was y equals 1. So this height is always 1. So the big R is from the center point on top all the way down to the bottom point, which has a y value of 0. So 1 minus 0 would be 1. The little r is from the center point, which again has a y value of 1, minus this inside point, which has a y value of 1 over x squared. So that's our little r. So my volume integral becomes pi times the integral of big R, which is just 1, squared, minus little r squared dx. And these are the bounds for x, and x ranges in this interval from 1 to 4. So to integrate this, 1 squared is 1. If I FOIL this out, I'm going to get a 1. I'm going to get a minus 2 over x squared and a plus 1 over x to the 4th, but I want the negative of all of that, so I'm going to need to distribute my minus. Whoops. So that's going to make all my signs change, and it's also going to make my 1's cancel. So I'll just have these two terms left, and I'm going to rewrite them, 2x to the negative 2 and a minus x to the negative 4, and then I can use my power rule. So this becomes x, when I add 1, this becomes a negative 1 over negative 1 times that 2, and when I add 1 here, this becomes negative 3 over negative 3. So cleaning it up just a little, this would be negative 2 over x minus, or excuse me, plus, because we have a minus minus, 1 over 3x cubed. So if we plug in 4, negative 2/4 is negative a half, and then this would be 1 over 3 times 4 cubed, whatever that is, and then if I plug in 1, negative 2 over 1 is negative 2, and when I plug in 1 into here, I'm just going to get a third. So then you get a common denominator, clean it up, do it all on your calculator, and you get 171 over 64 times that pi. Okay, on the next example, we have a torus. A torus is a shape that is formed by revolving the region bounded by the circle x squared plus y squared equals to 1 about the line x equals to 2, and we want to find the volume. So let's draw what this is going to look like. We're going to start with our circle, x squared plus y squared equals to 1. So that's just a circle with the radius of 1. And we're going to rotate that around the line x equals to 2, which would be over here somewhere. So when we rotate this around, the mirror image is going to look like this. And when you visualize this, this is a donut. Okay, that's what a torus is. It's just a big donut shape. Okay, so we want to find the volume of this donut. So how are we going to do this? Well, you kind of have your choice of what method you want to use. I'm just going to stick with shells since that's our theme for today. And since my axis of revolution is vertical, I'm going to take a slice parallel to that. So I want to take a vertical slice as well. So on the original circle, that would look something like this. And then the mirror image would be over here. And then I connect the top with a circle and the bottom with a circle. And that would be my cylindrical shell shape. And those slices are vertical, intersecting the x-axis. So this is going to be the integral of 2 pi r h, and it's going to be a dx integral. So let's find out what our height is first. So I'm going to find this point and find the length of that slice. That's always how you get your h, from that slice. They both share the same x coordinate, but the y coordinate is based on this circle. And we need to know what that y value is in terms of x, and this equation doesn't tell me that. So we're going to have to do a little bit of solving. We want to know what the y is in terms of x, so we want to solve this for y. So if I subtract x squared and then I take a square root, When you take a square root, you get a plus and a minus case. And that's important in this problem because the top half of the circle is the plus. So that would be this top half here is the plus square root case. And the bottom half of the circle is the minus square root case. And you can justify that or verify that on your calculator as well. So here's what I've got for my 2 points. The height is going to be the top y value, which is the positive square root, minus the bottom y value, which is the negative square root. They do not cancel out because you get a minus minus, so our height function is actually 2 times the square root of 1 minus x squared. So there's my height. Now we need a radius. So to get the radius, you pick a circle and you pick the center of one of your circles. So let's say that I pick this center here. My radius is going to be this horizontal distance, which is this x coordinate, which just so happens to be 2 because we're on that axis of revolution. So this x minus this x, and the x of this point was just x. So the radius is going to be 2 minus x. Remember that for shells, usually the radius is either x or y or some number added or subtracted from x or y. Okay, just some shift of x or y. All right, we have all the pieces. We're ready to plug it into our volume. This becomes 2 pi times the radius function, which is 2 minus x, times the height function, which is 2 times square root of 1 minus x squared dx, and then our bounds. Remember that the original region was this whole circle. So how does x range on that circle? It goes from -1 to 1. So we have here this integral. If you want to clean it up a little bit, you could pull out this 2 pi and this 2 and make it a 4 pi. But this is not going to be a simple integral to evaluate because of that square root in there. So this is one that I would use that function integrate command on. Type all this in. You could include the 4 pi inside your integrand or multiply by it at the end. Your bounds would be -1 to 1, and what you end up with using that function integrate is about 39.478. Okay? So let's make a comparison of all 3 of our methods. The discs and the washers. Now these use cross sections that are always perpendicular to the axis of revolution. So in the disc method, your formula is the integral of pi r squared, and it's either going to be dx or dy, and it'll be dx if your disc is vertical, hitting that x-axis, and it'll be dy if your disc is horizontal, intersecting that y-axis. For the washer method, your formula is volume equals pi times, and you can have the pi inside or outside of the integral, it doesn't matter, and you're going to have r squared minus little r squared, and this again is dx or dy. If your washer is vertical, like this, then you'll have dx. If your washer is horizontal like this, then you'll be using dy. The key thing to remember is that you take these discs and washers always perpendicular to the axis of revolution. That's the big difference between this method and shells. When you do shells, you always take your cross-section parallel to the axis of revolution, and you have a different formula. It's the integral of 2 pi rh, and this is either dx or dy. It's going to be dx if your slice is vertical so that your shell is vertical, and you're going to use dy if your slice is horizontal so that your shell lies sideways. Okay? So when do you use each method, and how do you decide which one to do? Personally, I think that discs and washers tend to be easier, but sometimes shells work better. So what do? Well, if it is difficult to solve for y in terms of x, which sometimes you need to do if you need a y integral versus an x integral, then you might prefer to do a different method. If the integral that you come up with looks really difficult to solve, then you might need to do a different method. Or if you need to use two integrals instead of one to solve the problem, then you might want to try another method. Okay, so these are all things to consider. If any of these difficulties pop up, then use the shell instead of the disk, or use the disk instead of the shell. So a couple of examples here to showcase these differences. Suppose that I have y equals x squared plus 1, x equals 0, y equals 0, and x equals 1 revolved around the x-axis. So this was exactly that very first integral that we did at the beginning of this video. So we have x squared plus 1, which is a parabola up here. X equals to 0 is the y-axis. Y equals to 0 is the x-axis. And x equals to 1 is just this vertical line. So we only want the portion of this region in quadrant 1. But when I rotate it around the y-axis, then I get this mirror image over here. Okay? So in this problem, what we discovered when we first did it originally is that washers were a bad idea, because up here you need a washer. But down here you need a disk. So if you do this with disks or washers, you would need two integrals, which means more work for us, which we don't want. So we don't want to do it this way. Instead, what we want to do is use shells. So if we take this region and we use shells instead, our axis of revolution is vertical, so our slice should be vertical. So our shells would look like this. So the height is going to be determined by these 2 points. They share the same x. The bottom point is on the x-axis, so its height is 0. The top point is on our curve, which had equation x squared plus 1. So the height is this y minus this y. So that's just x squared plus 1. The radius, if I look at the center of this circle, is this distance right here. And the x-coordinate of that center point is 0 because we're on the y-axis. So if I take this x-coordinate minus this x-coordinate, that means my radius is just x. So my volume integral becomes 2 pi rh dx, because this was a vertical slice going up and down. So this just becomes 2 pi times x squared plus 1 dx. And the original region in quadrant 1 had bounds of x from 0 up to 1. So those would be the bounds on my volume. So this is much, much easier to set up and solve, than doing it with two integrals. So this is easier, and it's the better option. So in this particular example, we'd prefer to use shells rather than disks or washers because we can do it with less work. Okay, well, let's see what happens with this example. Here we have y equals 1 minus x squared over 16, which is a parabola pointing down, up a height of 1, and it's a really flat parabola because it has this compression of this 1/16. And y equals to 0 is the x-axis. So I'm only going to draw that parabola up until the x-axis. So this would be the region bounded between this parabola and this horizontal line. And we're going to rotate this around the x-axis. So if I rotate that around the x-axis, then there's my mirror image. So if we did this with shells, my slice would have to go horizontally because my axis of revolution is horizontal. So I'd have to go this way. And that means the mirror image over here would look like that. And then I would have my circles on the top and the bottom. So because this is horizontally with shells, I would use volume equals 2 pi rh, and these would be dy's because this is going horizontal. So I would need to know this, And these 2 points, to get this horizontal distance going across, which is my height h, I need to realize that they share the same y coordinate. So I need to figure out what the x's are. And that's one of the difficulties of doing this problem with the shell method, because to find out what those x's are, it's not obvious and you have to do a little bit of work. So that might be something to sway you to try a different method instead. It is doable. If your curve is y equals 1 minus x squared over 16, we can solve this for x. We could multiply through by 16, so this would become 16y equals 16 minus x squared. Subtract, actually let's add the x squared over to the left side and subtract the 16y over, and then take the square root of both sides. And you do get a plus and a minus case. So the plus case is the quadrant 1. So that's going to be square root of 16 minus 16y. The minus case is the quadrant 2. So my height will be this x value minus this x value. And they don't cancel out because you're subtracting a negative. So they become, this minus minus becomes plus plus. So you get 2 square root of 16 minus 16y. So there's my height function. Now to get my radius, I would need the center point here, which has a y value of 0. So this y value up here minus this y value here would just give me a radius of y. So the shell method becomes the integral of 2 pi times this radius, which is y, times this height, which is this big square root. And then my bounds for y, from 0 up until where this hits, and that's going to be when x is 0, and when x is 0, this is at a height of 1. So from 0 to 1. So in my opinion, this is a lot of work, solving for x and getting this messy height function, and it gives you a tough, difficult integral to solve. So this is hard to integrate because of that square root in there. Plus it was hard to solve for in the first place. So that's why I would probably not use the shell method in this example, and instead I would vote for doing it with disks. So if we drew this region again, if you took your slice perpendicular to the axis of revolution, so I go vertically, then you have nice solid disks no matter where you draw them. So this is a nice disk method, which would mean the volume is going to be just pi r squared, and these disks are vertical, hitting that x-axis, so this would be a dx. So to get the radius, I just need these 2 points, and they share the same x. The bottom point has a y value of 0, and the top point is our curve. And the nice thing about the disks is, since we're using x's, I can just use this curve without having to do any sort of solving. So that's another benefit of this disk method. So my radius would be this y value minus 0. So my disk integral becomes the integral of pi, and my radius is 1 minus x squared over 16 quantity squared. And my bounds for x, where does this hit the x-axis? When y is 0, if you solve this, this hits at -4 up to +4. So those would be your 2 bounds. So this was easier to come by, and it's actually easier to integrate as well. So that would mean we'd probably want to use the disk method in a problem like this as opposed to shells. Okay, so getting something or having to solve for y, which would be too hard to do, or getting something hard to integrate would sway you to choose a different method. All right, let's try one last example. If I look at y equals x cubed plus x plus 1, which is a cubic function, you'd probably want to graph this on your calculator a little bit, and it has a y-intercept of 1, so it looks something kind of like this. Y equals to 1, this hits at 1, since when x is 0 this is 1, So y equals to 1 is going to go right through that intercept, and x equals to 1 is over here. So the region we're talking about is sort of this triangular region. And we want to rotate this around x equals to 2, which would be over here. So the mirror image is going to look something kind of like this. So my two options. If I wanted to do this with washers, because there's a hole in the middle, I'd have to use washers, then my axis of revolution is vertical, so my cross section should be perpendicular to that, so it should go horizontally. So I would have to do a washer like this. The big one goes from the curve to the curve, and then the inside one goes from the line to the line. And we would need to know this center point, this point here, and this point here. So let's see if we can find these coordinates. They all share the same height, so they all share the same y value. This x value is 2, this x value is 1, this x value is the curve, and it would be really difficult for me to take this curve and solve this for x because it's that cubic. So this is too hard to solve for x. And we would need to solve for x so that we could fill in what this should be in terms of y's, because using the washer method would require a dy integral. Pi times big R squared minus little r squared dy. So we would need to know what this curve is solved for x in terms of y, and I don't know how to do that. So that means that this is going to be impossible for me to do this way. But if instead I used the shell method, it might work. Okay, so here we would have that region looking like that. This is at 1, this is at 2, and then the mirror image, something over here. Then if I do it with shells, my slice is parallel, so I need to be vertical, just like my axis of revolution. So I would have a slice like that, the mirror image over here, circle on top, circle on bottom, and my height would be this point and this point, which is that vertical distance. And because these are both vertical lined up, they share the same x. So this top point is still on that curve, but because I now get to use x's, there's no need for me to solve for x in terms of y like I had to do in the other problem. I get to just use the formula as is without any solving. So that's why this method is better. This y value here is just 1 because we were on that horizontal line y equals 1. So my height will be this height minus this height. So the 1's cancel, and my height function h is just x cubed plus x. Then to get my radius, pick a center point on your circle. The x coordinate of this point is 2. I don't really care what the y coordinate is, because to find this horizontal distance, I'm just subtracting this x minus this x. So this 2 minus this x. So my radius is 2 minus x. So using shells, I get a volume formula that uses a dx integral, which made it a lot easier for me because my radius function was just 2 minus x, and my height function, I got to just use the formula of my curve without doing any solving. So here's what the integral looks like. The bounds here, for x of this original region, I went from 0 up to 1. And so this isn't very hard to solve. It was fairly easy to set up. So this would be the better option than doing it with washers. Okay? All right, this is called cylindrical shells. Take some practice drawing these pictures, but make sure you know all the formulas and make sure you remember the differences in how you take your cross sections, whether you're doing shells or discs or washers. Good luck.